What we are going to do now is take that rate law and look at the different orders and see what happens over time. Here's the deal. I don't want you to get too caught up on all the math that is going to happen. I don't want you to get frustrated because it's calculus and we're going to do some derivatives and some integrals and things of that nature. We are pretty much going to look at the end product, but I just don't want to jump from, there are the tables, these are the equations we're going to use without you kind of getting a small idea of how we got there. So we can take that rate law and do a differential rate law, which just describing a single movement in time. It's a static situation, a static relationship between rate and concentration. So that rate is the derivative of the concentration over time. Now, if we want to do it in a continuum spectrum, which is just not just a static, we call that the integrated rate law, when we look at it as a function over time. And we can then use that to predict the value at any time. So what we're doing is taking a snapshot and taking it up into a more continuous situation, which makes more sense and is more flexible in terms of the calculations you can do. Now, we are concentrating ourselves on doing this only for zero order, first order, or second order. And we can take those equations and we can find the derivative over time and equal that to the constant times the concentration in some cases, because the concentrations will be constant as well. So a derivative of a concentration over time for each one of those orders. It's not just quite simple like that. Because when we decide to do it that way, we have to separate the variables. We want one side with concentration, one side with time. Because by doing that, it will let us integrate to some limits better than having two variables together at the same time. So one side for concentration, one side for time. By separating the variables, then we can do a derivative, which you do in calculus, and you spend a lot of time doing that there. We are not going to spend the time here. But when we do that, there's some things we're going to have to do to the concentration, so manipulate the concentration. For zero order, because the concentration is not there, so it's just a derivative of concentration. But for first order, we had to divide by the concentration because we wanted to keep that concentration on one side versus the other. So we are taking the equations that we took before for the rates, and now we are separating to both sides. And in some cases, that concentration gets squared. Other cases, it's just divided, and zero order, that concentration has no effect on the equation. Then once you separate those variables, you can do an integral. If you took calculus, you know what that means. The integral is just going to integrate that derivative so you can see what happens between an initial value and a final value. So you get some limits, and it's a continuous function. So this in here right now is a function of concentration over time that we are integrating for any situation that we can have. Let's see what happens now. We can look at those derivatives and integrals for concentration for each one of those orders. And for the zero order, it's just a concentration of the substance. For first order, is going to be the natural log of the concentration, and for second order, is going to be -1 over the concentration. Now, If you're not lost already, we're doing that for concentration. We will also have to do it for the time. And that will take certain, it will look in a certain way. We can put all that together by applying the initial and final limits, which I'm going fast through this because I don't care on how it looks. What I care is that I'm going to get some equations at the end for each one of those orders. Those are the integrated rate loss functions for each one of those orders. And those are the equations that you have in the reference tables that I gave you. So we had to do all that math to get these three equations that you do not have to memorize because you have a reference table that have them. And that table includes what the rate law for that order is, how the equation over time will look like. You have something else that is called half-lives. We'll look at that in a little bit. And then the units for the value of K for each one of those orders. And that's what I've been saying. If you know what the units are for K, you pretty much know what the order of the integrated rate reaction will be. We can also do, because this is all is an equation, equations can be plotted because we have two variables. We have concentration and we have time. So if it is a zero order, I plot the concentration versus time, and you get a decreasing straight line. For first order, I'm going to plot the natural log of the concentration over time. It's also a decreasing line. And for second order, is just 1 over the concentration versus time, and that's an increasing straight line. So what we've done is taking the rate law equations for 0, 1, and 2 order and using integration and differentials, come out with an integrated rate law that takes into consideration of the continuous effect between two limits and time. Okay, I am not going to solve it here, but in that spot check handout that I gave you, if you look at question number 4, it says kinetic data was obtained for the reaction. You have the reaction and you have time values and concentration values. What is the order of that reaction? And what is the rate law? So how do I do this? Because I have concentration and time, I'm going to go, let me go back in here. I'm going to plot concentration versus time and natural log of concentration versus time and 1 over concentration over time. And you are going to get 3 different graphs. The graph that gives me the straight line gives you the order of the reaction. So it has to be a straight line for you to know what the order will be. So let's say I plot the data and the straight line tells me it's first order. What that means is that if the plot for 0 and second order are not going to be straight lines, are going to be curves. If it is a second order, the 0 and the first are going to be curves, but the second order will be a straight line. So by looking at how that graph is plotted, as long as you get a straight line, that's the order of the reaction. I will be asking you how to, I think I have an example that I will be giving. If I have time, I'll do it. If not, you have it on Canvas. I have some examples in there with the answers that you can take a look at. But this problem number 4 in the spot check, you have to plot the data and from there determine the order, and then calculate the value of K. So how will you calculate the value of K from a graph? If you have an equation, it will be what? It is a straight line, so it will be the slope, because it's a change. So the graph gives you the order as long as you can pick which one gives you the straight line. The slope is going to give you the value of K. Okay, any questions on that? Yes. I am not going to test you on how to get the equations. I will test you on how to use the equations and to identify what the equation that you will need to use is. I can give you the units of rate for this equation. For this reaction are so and so. What order is the reaction? By looking at the units, you can tell me what the reaction order is, because you can go to the table and look at the units and see what the order is. Okay, I have these graphs in here. What is the order of this reaction occurring based on this graph? Okay, so if I have 3 graphs, look at the one that with a straight line, look at what I'm plotting, and that tells me what the order is. That's the second way of doing it. And the third way is, okay, if the initial concentration is this, calculate the final concentration if the K value is given. So now you have to use the equation to calculate a final concentration. So those are the 3 different cases I can give you. And I have examples on all that here. So any other questions before I move on? Because I had some examples, I will go through those. I think it's better if I do, instead of letting you